We've been talking a little bit about maxes and mins, and what we found last time was local maxes and mins, and wanted to mention here the idea also, absolute max and min. We recall from two-dimensional, this is now two-variable or three-dimensional functions. We were doing two-dimensional functions. When we went to absolute maxes and mins, of course, if we just have a regular function where x is whatever it could be, just based on the function itself. In this case, what do we got for absolute max and min? No absolute max, right? But we have an absolute minimum at that particular point right there. However, when we close it off, say we want a closed interval of this particular function, and let's see. If I go from 0 to here for this function, so I'm only talking about this on this closed interval. Now when we talk about absolute max and min, we still got the same absolute minimum, right? There's an absolute minimum at that point. But now we have an absolute maximum, and it occurs at an endpoint, right? And so when we talk about absolute maximum, then the absolute minimum here is we could say it's at a critical number, right? Critical value. Okay, yeah. But as far as absolute maxes and min, there's two scenarios. You can have either an absolute extreme at an endpoint or at a critical number, where the derivative is 0 or does not exist in the case of two dimensions. Well, the same is true when we go to three dimensions. For z equals f of xy, absolute extremes can happen, extrema, can either happen at a critical point. We call them critical points because you've got an x and a y there. Critical points, or technically, when we've got x's and y's, and so think back, on our domain, when we did our domains, we had, in certain cases, we had whatever x and y could be, and it may be specified here, but our domain is whatever it is. I mean, I'm just making that up, but say that's our domain. Well, what you have to check, just like you had to check the endpoints here, you got to check the boundaries of your whatever region you're talking about wanting your minimum over. In this case, if it was negative infinity, positive infinity, that was one thing, but we specified here a domain, if you will. So if we specify a region, we need to look at the boundaries, because that's what, boundaries, that's kind of what we call them endpoints, but on this we have to phrase it more boundaries. So you look at absolute extreme happen at critical points or on a boundary point of whatever closed region you happen to specify, okay, or that is specified. All right, so let's find some absolute extrema here. We've got f of xy equal 2x plus 2y minus x squared minus y squared. And we want to find that on set D, which is going to be the closed region, the closed triangular region, with vertices 0, 0, 0, 9, and 9, 0. Okay, and so if we just look at that region, here's what we're talking about: 0, 0, 9, 0, 0, 9. Okay, so that's the region we're bounding this by. So we're just looking at, for this graph, not sure what it looks like, but we're just limiting our xy values, if you will, to this. Okay. So, to find the absolute extrema, we said we need to look at the critical points, and then we need to look at boundary points. So let's, first of all, get the critical points. Find the critical points with partial derivatives, okay? So partial with respect to x, that's going to look very similar in both of these, isn't it? 2 minus 2x. And so we need to set that to 0 to find the critical point, and that would be x equals 1, right? And very similar for the y, we'd have 2 minus 2y. So set that equal to 0, we'd have y equals 1. And so that's our critical point, right? 1, 1, which, notice, is in our bounded region there. So it would be one point we're going to need to check. All right. Now, just like in our two-dimensional case, we do need to check the endpoints here. So the endpoints are 0, 0, 9, 0, and 0, 9. The endpoints, you know, just like we did. Where do we check them? Well, we're checking for the maximum and minimum values. So what we're going to do is we're going to plug these values in. 1, 1, we're going to plug it in, just see what value it gives us. 0, we're just going to plug those in and see what values those give us. But we also have to, those aren't the only boundary points, right? Because there's also boundary points along these lines. Let's call this line 1, line 2, and line 3. We need to check those lines also for potential maxes and mins. So let's check along the boundaries. I mean, these are boundary points too, but they're endpoints of the boundary point. Yeah. So on line 1, what have we got for as far as xy values there? Well, that's along y equals 0, okay? And so the points along that are 1, 0, 2, 0, 3, 0. So the points there are of the form x0, right? So let's get our function in terms of fx0, which would be, what, 2x minus x squared, which is just another function, so we need the critical numbers there. The derivative is just 2 minus 2x, and so that would be, again, x equals 1. But in this case, we've got the y is 0, so that would be what point? 0, right? X is 1, so I'm going to check 1, 0 on that point, because that's the critical value, critical number when we're along this boundary. Okay? So we need to do the same thing for line 2. On line 2, well, the points are, you got x is 0, so the points would be of the form 0y, right? Because x is always 0 on that one. And so we've got basically the same thing in terms of y. If x is 0, then we've got 2y just minus y squared, which the derivative of that would be 2 minus 2y. Yeah, then you just do the derivative, because you're trying to find the critical numbers where you might have a maximum or minimum. And that's, well, it's just the derivative of it, yeah. And in this case, it's all in terms of x. So the derivative of that would be 2 minus 2y. Y equals 1. So that's 1. Last but not least, then we've got to check this line. So in line 3, what do we got? Well, we've got a different line, don't we? If you do a y equals mx plus b, the b is 9. The slope, -1. Okay. So on that case, we could say the xy, couldn't we, as x comma negative x plus 9? Just to get it in terms of an x. So that would mean we have the function is 2x plus 2 times negative x plus 9 minus x squared minus negative x plus 9 squared. Which is 2x minus 2x plus 18 minus x squared. That would be minus, what, x squared minus 18x plus 81. So that'll be negative 2x squared, 2x's cancel, plus 18x, 18 minus 81. 18 minus 81 is 63, is that right? Negative 63. But we're going to take the derivative anyway, so the derivative of that would be, might need to go over here. All right, so the derivative of this function would be negative 4x plus 18. So we set that equal to 0, and that gives us x equals negative 18 over negative 4, which is 9/2, which that would make the y, since y is 9 minus x, 9 minus 9/2, which is 9/2, okay? It would be 9/2, 9/2. right there. Okay, so here's what we got. We got 1, 1. Then we've got these endpoints, the corners. And then you've got 1, 0, 0, 1, and 9 halves, 9 halves. So our absolute max and min, that's where those are going to have to occur at one of those values. And so really all we're going to do next, I guess I'll have to erase here. Really all we're going to do next then is evaluate our function at each of those values. Of course, I know it's not going to be that, well, it may be that. Let's see, what are the other ones? One, 0. Yes, yes.
You're not actually
right. Well, I mean, it just works out. Yeah. That's right. Okay, so let's see. 1, 1, that'd be 2 plus 2 minus 1 minus 1. 4 minus 2 would be 2. 0, 0 would be 0. 0, 9. The x is 0, so it'd just be, what, 18 minus 81. So negative 63. 9, 0, we'd have 18. Again, minus 81, so that would be negative 63. 1, 0 would be 2 minus 1 would be 1, 0, 1, also 1. So the trickiest one will be that one, be 9 halves, so that'd be 9 plus 9. If we plug in 9 halves, doing it quickly here, so check me if I'm wrong there. Minus 9 halves squared twice, right? Which is 18. I had to bring my calculator. Okay. Which is 40, which is a negative number, but it's not more negative than that one. So here's our maximum. And here's our absolute minimum. Or that one, if you want that one. Okay. Yeah, so it just complicates things as before, just a little bit. Not too bad, but. Question? Well, it's just the smallest value out of these, right? Yeah, well, that's what I said. You could take your pick here of either one of these. Yeah. Yeah, these are both your absolute minimum.